Hey everybody, today I start isomerism in the organic chemistry. Isomerism is two or more compounds with the same molecular formula but different structure. Okay, we can classify in two types: constitutional or structural isomer, or the second one is true isomer. Constitutional or structural isomer is divided for the three types: regio, bounding, and tautomerism. Okay. Now I continue with the constitutional isomer. The first one is the regio isomer. Okay. As you see, the position of the bound is different, but functional group is the same. You see, it is a butane. It is a isobutane. Both of them are alkane, but in the different structure, or one color propane or two color propane is the, for example, or I can write other example. For example, if you see here, one butane, and two butane. You see, one butane and two butane. The second one, bonding isomer. As you know, the bonding system change. Usually, the functional group also change. For example, if you see here is the alkane, here is cycloalkane. Butene, okay, both of them has a C4H8. It is alkene, it is a cycloalkane. Both of them has the same formula, but different structure. It is function group is alkane, it is function group is cycloalkane. Or, for example, relation between the alcohol and ether, ethanol or dimethyl ether. It's very easy, okay? In the bounding isomer, usually the functional group change. It's very important. And for example, we can write relation between ester and the carboxylic acid. For example, if you see here, I draw this ester. It is a methyl propanoate. It is the same isomer, bounding isomer with the butanoic acid. Both of them has a 4 carbon and 3 is 8 hydrogen, 3 2 2 1 8 hydrogen, and it has 2 oxygen, both of them. And the last group is tautomerism. Tautomerism, when the position of pi bond and the hydrogen, the alpha hydrogen change, because we know this is alpha hydrogen, because it is close to the functional group. If this hydrogen go here and double bond come here, it will be tautomerization, and it is between the oxo-anol tautomerization. It's very important things, and we have to know about this. And because it's oxo group, also we can say keto, we can say oxo-anol tautomerization, or because here is the keto and here is the anol. We know anol is the type of alcohol which carbon bind, OH bind to the carbon with the sp2, and in this situation we will be oxo-anol tautomerization or keto-anol tautomerization. Now we go to the stereoisomer. Stereoisomer divided in two groups: conformational, as you see here, and configurational. Now we go to the conformational. Conformational is very important. It is the stereoisomer. Stereoisomer, the isomerization, the chemical formula, and the bonding between the atoms are the same, but the position in the 3D, in the space, is different. And the conformational isomer, okay, is the spatial arrangement of different atoms or functional group in a molecule which are not bound directly to each other. Okay, it's very easy. For example, we have ethane. In the 3D space, we can show in this structure or we can show in the Newman projection. As you see, if we look at from this direction to this carbon, we can see this carbon here. But we cannot see this bound because it is exactly behind this carbon. And we can see this hydrogen, and this hydrogen. And we couldn't see if exactly the same position, this hydrogen, and we put inside the parentheses. Okay? As you see here, in this situation, these hydrogens are closer to each other and high repulsion, high energy. Because it has a high energy, in some situation we have a torsional strain, we will study later. But the repulsion is high, the energy is high. We say this conformation because of it is the eclipse conformation. Okay? But for the conformation, we can rotate sigma bond. You see, in the conformation, we want arrangement. Okay, for arrangement, we can rotate sigma bond. Then I can rotate this bond. When it rotates, these hydrogens go here, this go here, and this go here. And we will have this one go here. One of them we can rotate, okay? It will be this shape. And if we see it again from the same direction here, we see these hydrogens will be in the 60-degree direction here. And as you see, the distance between the hydrogens will be increased. For example, now more distance between these two hydrogens. And the energy will be decreased, lower energy. And we can show in the Newman projection, in this shape is Newman projection, is staggered. The angle of rotation, we usually rotate 60 degrees. Because if we rotate 3 times, it will be 180. And as you see here, with every rotation, if we imagine it's the 0, it's the 60. And in every rotation, excuse me, it is a 0, it is a 60. In the 0, we have an eclipse, higher energy. Again, rotate, we have a stagger. Again, eclipse. Again, stagger. Again, eclipse, stagger. And we can go the same. Because it's ethane, it's a spatial case. Because all of the branch, or it is the hydrogen, in the rotation, we can see the hydrogen and repulsions and will be the same. Okay, it's almost in the symmetric in this case. But if we study conformational isomer of the, for example, butane, okay, but between C2 and C3 rotation, because it's very important. In the Newman projection, if you see, if you look at from here again, we will see 2 metals in the up, and because you see these 2 metals behind each other, these two metals behind each other, and this hydrogen behind each other, and this hydrogen in this direction, we say sim periplanar. Okay, it is eclipsed. Okay, because it is behind each other, we study not staggered, but it is highest energy. Why? Because the repulsion of 2-methyl is higher than between 2 hydrogen, because methyl is big. Okay, then I have to choose this position for the here. If I rotate 60 degrees, I will see staggered, but this is staggered is the synclinal. The Again, two methyl almost close to each other in the stationary pose is the gauge. Then it will be lower energy, but it's still too. It's also if compared to the other type of the stationary, it's almost high. Then we can choose in the gauge this position. Okay, again I rotate 60 degree, will be again eclipsed, but if you compare the simple planar and anticlinal, you see here two methyl repulsion, here one methyl and one hydrogen. We know two methyl is bigger and high repulsion is higher, but in the methyl hydrogen repulsion is lower. Then it is both of them is eclipse, both of them high energy, but this one is higher than this one. Then if compare these two, you see this is higher. If again rotate 60 degree, we again reach the staggerd, but this is staggerd, it is anti-perpendicular. Two metal is in the highest distance compared to each other. Then it will be lowest energy. In this situation, we will have this position lowest energy. Again, if we rotate again, we will reach the again to anticlinal. Okay, the energy level must be the same because the same situation. And if we rotate 60 again, we have again staggerd, and we will reach again gauge. Okay, the staggerd lower energy, but compared to the anti-periplanar, its energy is higher. And in the last situation, we reach the symperiplanar. In this case, energy will be higher, like 0 degree. Now, if you see 60, 120, 180, 240, 300, and 360 is the last position in the conformation of the butane. Also, in the conformation of the isomer, we can also compare to the cycloalkane. For the cyclopropane is a special case because angle is 60 degree, but we know the sp3 angle must be 109.5. As you see here, because in the mathematic form, the angle of the triangle is 60. Okay, 49.5 degrees is smaller, and it can make an angle strain or Bayer strain. It increases the energy, okay, and it can cause the hydrogen of this cyclopropane are in the eclipse always, not staggerd. Highly reactive, okay, because of this energy, and because of repulsion and the higher energy in the hydrogen of all our eclipse, it's a torsional strain or pitcher strain. And because it is very reactive, reaction mostly with ring opening can be happen. For example, if I have a cyclopropane plus Cl2, in this case, we will have a bond opening from here. One Cl bond this area, one to this carbon, one for this carbon. And it will be 1,3-dichloropropane. Cyclobutane compared to cyclopropane is better, and repulsion is lower, angular strain bias are lower, torsional strain is lower, or pitch strain is lower, because the angle is 88, but it has a torsional strain, okay? And it in the shape, you see, it is like an envelope form, and it is not planar. But compared to the cyclopropane, it has a higher stability, lower energy. And the last one in this group, cyclopentane, the angle is 105. But compared to both of the cyclopropane and cyclobutane, the angle is with the sp3 109.5 is the difference not so much, and it's very stable compared to the others. Then we can say we have high stability in the cyclopentane. In the next lecture, we will study about conformational isomerism of the cyclohexane, which is one of the most important case. And I hope it will be good, and see you in the next lecture, and have a good time.